So in all the cases that we have seen, we are solving an equation in the following form. A, B equals C. And now it depends. If C is a column vector, then we are dealing with a system of linear equation. Then if C is the identity matrix, then we are finding the inverse of A. And if C is general, then it's a matrix equation. And now I'm going to show you what is the trick to remember how to solve this situation by putting an example in 4 dimensions where you will see the systematics of the procedure. So let's say we are going to look at the general case now. We went from simple to complex, and we are going to see the complex and see how it translates to other cases. So in a 4-dimension case, so A equals A11, A12, A21, to A44. Okay? And now we have similar for B, which is the incognita, and then C, capital C equals the same, C11, C12, C21, to C44. So the key here is the following. We get the columns of A, and we form the vectors R sub I equals the sum over J of A, J, A, E, J. So this should be equal, for example, to E A1, E1 plus E2, E2, and so on and so forth. These are the vectors that we formed before, and now we make the following construction. So I'm going to make this a little bit more space because I will need it here. So this will be step 1. And then the step 2 is immediately we get the coefficients by the following construction. B11 will be equal to R1, R2, R3, R4 minus 1. This is the determinant of the matrix A, remember. And then B21, B31, B41. And the prefactor is going to be always the same, so I will summarize it as the thing between parentheses minus 1. And here is where the beautiful tricks come through. We get this object, and we paste it here 4 times. Fantastic. And now we are going to define, so we define the R's in green here, and now we are going to define the C's. And the C's are exactly the same as before, the columns of C. So we define Ci as the sum over J of C Ji E sub j. Okay, here is a separation. And I'm going to case this because these are the important constructions that you're going to do. And I'm gonna erase this example because you have seen it already. And this is a little bit more clean. It's important to be organized when you do math. And now what we do is we delete the first object, the second object, the third object, and the fourth object. And now we substitute it by C1, 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 C1. 1. And there you have it. These are the solutions for the first column of B. And to get the rest of the expressions, we copy all of these. We leave it in there. And then we paste it here. And now we can do the following. So where we had here a 1, now we put a 2. And then we switch here a 2. And we get the solution for the second column of B. And so on and so forth for B1, 3, B2, 3. And this is how you solve a system of general equations. Now, how do we apply this to the cases that we saw before? Well, very easily. If C equals to the identity, so we are dealing with an inverse problem, then the only thing we have to take into account is that C1 will be equal to E1, C2, E2, C3 equal E3, C4 equals E4. And there we substitute in these expressions here, 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 and we obtain the solution. And if we are dealing with a system of linear equation, for, let's say, linear equation, is the case where C equals a C vector and the rest is zeros. So this is equal to C1, C2, C3, C4, and then we simply have to get one of these expressions. So we will get, well, in this case, of course, B, let's say, is also x1, x2, x3, x4, and then our solution will be given only by one of these blocks of solutions, which I hope it fits here. Kind of, yeah, it fits. So now we have to simply delete these and these ones and say that this is x1, x2, x3, x4, and here we have a C, 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 and C, which is this column vector C. And with this technique, we have beautifully unified how to solve matrix equations, how to obtain the inverse of a matrix, which obviously is a particular type of matrix equations, and we have introduced a very useful and beautiful way of producing solving systems of linear equations. Now, as I said in the first lecture of this module, I will not use these techniques to solve a system of two linear equations because it's a little bit cumbersome and long, and I will rather do a substitution and solve it. But having a systematic system that works for systems of any dimension or allows you to calculate and program, for example, in a computer, how to obtain the inverse of matrices of any dimensions without restoring to the calculating the adjoints and the cofactors, etc. It's a very, very, very powerful system. Moreover, because as I said before, it unifies a lot of definitions that you have to introduce by hand when you work with standard linear algebra. As a last comment, I don't know how well this performs numerically. That would be a very interesting thing to consider, because we know that obtaining the inverse of a matrix, for example, is a very hard computational problem when we go to matrices of many dimensions. So I don't know how current techniques compares in terms of computation time with this system. I will not bet too much into it because this is a very nice algebraic technique, but current numerical systems are very highly optimized for the programs that run currently, so it might be the case that run even slower, but it's a extremely nice and powerful tool to algebraically solve these solutions. So I hope you liked it, that you found it as interesting as I did, and incredibly simple, because I will not expect at first time that for geometric algebra to provide also tools for the systems of linear equations. But indeed, it is very characteristic of geometric algebra to pop up in basically any realm of mathematics or physics that you can think about, and greatly simplify or unify the different techniques that we have.